Hi, welcome back to this video series on program synthesis. In this session, I wanted to quickly clarify a few things that were not elaborated in my previous demo of synthesizing a function that will divide a given number by 16. For example, I would like to have a function f, right? The function f will take my input a, right? And it will perform a division by 16, okay, integer division. Okay, so a can be a negative number, a can be 0, a can be greater than 0. So I would like a function like this. However, the constraints are as follows, right? You're not allowed to use the division operation, right? You're not allowed to use, in the programming world, we use a slash. We are not allowed to use if then else statements, right? So no if something, then that kind of thing is not allowed. No conditional statements, just to avoid branching. Then the third constraint is very important, right? There should not be any overflow, right? If you do bitwise addition, for example, you may overflow because of finite arithmetic in computers, right? So no overflow is allowed, right? You are not allowed to use the division symbol, no if then else. These are the constraints. Okay. So I talked a few ideas during my previous session. Today I will spend a little time just focusing on division by 16 and how we can synthesize it. Okay, let's think about what happens when we just use the right shift operator, right? In the past, we looked at unsigned operations like division. It was much easier, right? All we have to do is take the number a and right shift it by 4. This will give us division by 16. But this is not going to work when a is a signed type, okay? What I mean by that is, say, for example, let's assume we are working with 8-bit numbers. Let's assume a is an 8-bit number for a moment, okay? So what if I wanted to figure out what is the value of, say, minus 33, right? Division divided by 16, okay? In the C and the Java programming languages, usually the answer is, as far as I know, is minus 2. You basically divide it and throw the decimal part. Okay, that's basically how the divisions are programmed. Okay, so how do we get minus 2 when we use this operation? Okay, can we check that first? Well, we can check it quickly. I already computed the binary representation of minus 33 to save time. So minus 33 is nothing but 1 0 1 1 1 1 1. Actually, you can check very easily, right? Because there are, how many I have? 5 plus 3, 8 digits. Only the 0 1 2 3 4 fifth index starting from the right is 0. What is the weight of the fifth index? The fifth index contributes 32 to the weight, right? So I am basically taking away that 32. If all the bits are 1, then you would have a minus 1. Therefore, minus 33 is the correct representation. Okay, this is minus 33 in binary. What happens if I just do right shift by 4? That means I will be getting rid of these 4 bits, right? And let's assume I'm doing arithmetic right shift, right? So let me write it here like this way: minus 33 right shift by 4. So what it means is that you get rid of the last 4 rightmost bits, right? So you will be ending up with 1 1 0 1, right? Because these 4 will go away, right? And then because of the arithmetic right shift, this is arithmetic, right? We need to repeat the most significant bit in the first 4 places, right? So okay, what is the value of this expression? As I said earlier, this is easy to compute also, right? So you have all ones except the index which contributes the weight of 2. Therefore, this must be equal to minus 3. Okay, so what's happening now is you got an answer minus 3, which is wrong because, as I said earlier, the answer should have been minus 2. Okay, this is the expected answer, but the answer we get is -3. So we can't use the regular right shift, arithmetic right shift to get the division by 16. So shall we synthesize this using program synthesizer? Of course, that's the whole purpose, and I'm going to show you how we can synthesize automatically, right? That's my plan now. And I will explain a little bit detail about how to interpret the synthesized program. Okay, that's my plan. Okay, so here is the synthesizer, right? So the synthesizer doesn't have if then else statements. As you can see, I only allow and or not, shift left, shift right. And of course, I need to specify how much of the shift amount is allowed. I'm working with 8-bit numbers, right? Therefore, shift is bounded from 1 to 7. What I'm expecting the program to do is the program constructs division by 16 for me. That this is the specification, right? This is same as using the BVS div operation, which is basically built inside this language. This is the specification part, but we wanted to synthesize the implementation of division by 16. Okay, how do we do that? Well, this is basically it, and let's run it and see what happens, right? And then we will discuss the model that's coming out, program that is coming out. So it's working hard on our grammar to come up with an implementation that will match the specification we gave, right? The specification we gave was division by 16. The answer that is computed by this program better be division by 16. Okay, program. So we will see how that goes. Okay, here it is. So the function is shown here, right? This is the synthesize function. So let me write it in a regular syntax so we can quickly discuss this, right? So what it has synthesized is basically division by 16 function, right? Let me call it f of x, f of a, for example, which is nothing but, let's start reading this thing. We are going to do from the deepmost operation, which is bit vector shift right, arithmetic shift right, right? So how many are we shifting right? By 3 positions, right? So the innermost one is a shift right by 3 positions. Okay, this is arithmetic right shift. Okay, and then we are doing a logical shift right. How much are we doing? We are doing it for 4 positions, right? So we take this answer and we do a logical right shift. Let me put L here for 4 position, right? 4 position. Okay, this is the logical right shift, 4 position. Okay, so what is the next thing we are doing? After that, we are adding A to the answer, right? Okay, and oops, sorry, we are adding A to it, and then we are doing a shift right by this whole thing, shift right by how many? By 4 positions. Okay, so this is basically, and this is also arithmetic because you see an A there, right? Arithmetic right shift. So this is the expression it came up, and let's see whether we can make sense out of it. Of course, this is correct because we formally verified, assuming there is no bug in the verification engine. This is correct. But let's try to make sense out of it. So what is it trying to do? So what is the meaning of let me start here, right? What is the meaning of when you do a right shift by 3 position of a signed number? Okay, remember the signed number, if A is a signed number, the most significant bit is 1. Okay, so when you right shift by 3 positions, you're basically getting rid of 3 least significant bits, right? So what's going to happen now is that the first 3 positions are going to be empty, right? Because you're getting rid of your rightmost 3 bits. So what's going to happen is you're in a situation like this. Your A will have the first three place empty, right? So this is empty, this is empty, and this is empty. But what is the fourth place value, which is 1? Because remember, a is a signed number. Therefore, after doing the right arithmetic shift, this will be 1. So the question now is, what shall we fill up here? Which must be obvious because we are doing an arithmetic right shift. So when we do arithmetic right shift on a signed number, we are guaranteed to have 4 ones at the beginning. Okay, we don't care about the rest. Okay, we don't care about the rest. What is the next thing we are doing is we are doing a right shift of this data again, logical now, by 4 position. Okay, so what will happen now is that we have well, we have to do a right shift again by 4 position, but this time it's logical, right? So we will be getting rid of the, okay, let me finish this then. 5th bit, 6th bit, 7th and 8th bit, right? So when we do logical right shift, what will happen? These 4 bits will disappear and the 4 ones will come here. So we'll have a new state, 1, 1, 1, 1. And the old state, well, these places will be 0, 0, 0, 0. So this is the new state after we performed both the shifts. Okay, and now next step is to add a to it. Okay, so what is the meaning of adding a to it? Well, this is basically the some people call this as a mask. Okay. Remember, whenever we deal with signed numbers during division, we add some quantity. Otherwise, the round off will be on the wrong direction. We want things to round off towards the 0 direction, right? That's the reason why we add the mask when we do the signed division. So anyway. Okay, so this is the state we have, right? This is the new state we have, and now we add a to it. Okay, and when we add a to it, what is the new number we get? Okay, so one moment. So this is the state we are. What is the purpose of adding a to it? Well, we add a to it so that the number is actually pointing to the 0 direction when we finally compute the right shift by 4 position, right? What is the meaning of right shift by 4 position? Okay, right shift by 4 position it means that you get rid of the last 4 bits, right? The least significant bits. But what is the meaning from a division perspective? It means that you're dividing it by 16, right? So what we are trying to do though is that after we computed the mask, this is the mask, this whole thing, right? What are the possible values? Well, we can see this, right? We got rid of the last 4 bits here, the least significant bits. We managed to transfer the 4 ones toward the end. What is the weight of these 4 ones? Okay, maybe that's basically it. If these 4 ones contribute the weight of 15. Okay, so basically we are adding a to 15 here. So this whole thing is a plus 15. So remember when we did divide by 2, we added by 1. Divided by 4, we added by 3. So essentially, we have to add 1 less than the amount that we are trying to divide by to get this into the right direction, pointing towards the 0 direction. Okay, that's basically it. So this 15 number magically came out of this this particular block of operation. Okay. And once you add 15 to it, what is the next step we are going to do? We are going to do arithmetic right shift of 4, okay, which means you are dividing the result by 16. So essentially, this is going to be divided by 16. That's basically it. So what we actually did is we let the computer came up with this expression for us, right? This is it, right? However, the numbers 15 and 16 are not appearing directly on the synthesized program. Nowhere here you see 16 and 15. So I will show you a small trick you could do to synthesize much more compact program if you allow a little bit of more flexibility in specification, okay? So what I mean by that is, let me show you the details. So let's go to the code again and do a small change, okay? Which will allow us to do much more efficient or compact rather, not expression. So let's assume we allow some constants, okay? What kind of constants we would like to allow? Usually the interesting constants when you do bitwise operations are, you know, the bits like FF, you know, all ones, all, something like this, right? Usually these are all good constants, so you can add. So I'm going to add a few of these. Let us see what happens when we add these constants. Can we get more compact representation? Okay, so you will see. Sometimes we may, sometimes we may not. Maybe I didn't do okay. Maybe I made a mistake. So it's synthesizing a new expression. Hopefully it will consider our constants. I cannot guarantee you. Okay, it is taking some time. Maybe I should go back and sort of comment some operations and see whether introducing the constants might have slowed down, right? So let's try something alternative here. So I'm going to do this. I'll, for a moment, say, since we are doing unsigned, let's say we avoid logical SIPs, okay? Let's see whether this helps. I cannot guarantee this is going to help, but my goal is to be able to sort of come up with more compact expression than the one that was synthesized earlier, just out of curiosity. The one that it came up at the first place is already perfectly fine. Yeah, I'm just curious whether, yeah, so something different this time. It took, okay, let's see. We can synthesize this a little bit more. We can rewrite this into our notation, right? And let us see. What is the function it synthesized? It synthesized something like this, right? F of A is equal to your innermost one. What is the innermost one? Is shift right by 3, 4, 6, 7 positions, right? So shift right by 7 positions. Okay, 7 means you get rid of all of the bits except the most significant bit, right? We are doing arithmetic right shift. So we are only working with 8-bit numbers, but we can easily generalize it to 32-bit because the same structure holds true anyways. Once we confirm that this is independent of the bit vector size. So we have our A right shift by 7 positions, and then we are going to do, what are we doing next? We are doing a bitwise AND with, what number is that? This number is, remember, this is F, okay? So we are going bitwise AND with F. So what does this mean? What does this mean? This means you're going to extract only the last 4 bits, okay? That's the interesting part. And then it's the remaining part is the same as the previous one. We are adding A to the expression, and then we are done, right? And then we are doing a right shift by how many? By 4. Remember, right shift by 4 means division by 16. Okay, so Let's think about this mask now. What is this mask that you're seeing? Okay, well, if A is a signed number, what is the meaning of the most significant bit, or what is the value of the most significant bit? It will be 1. When you do right shift by 7, all of the resulting bits will be 1. Therefore, you have 1, and bitwise F will give you an F, which means F is 15, which is exactly the value we should be adding to our number A. So that's basically it. Suppose assume A is an unsigned number. When we do right shift by 7 position, we get rid of these the 7 least significant bits, but it will be all 0, right? Because we start with 0. So 0 under something is 0. So we are not adding anything, which is what exactly needed when we have an unsigned number. So all we are going to do is be taking the A and directly doing a right shift with 16. Okay, so this is much more compact than the previous synthesis. But remember, there are some fine-grained differences, right? From a grammar perspective, what is the difference? The difference is that you are basically now specifying constants. Okay, you may wonder how I came up with these constants, but I just list some common constants people often use during these kinds of operations. If you allow the system to explore all possible constants, it oftentimes wouldn't stop. So I will show you what I meant by that. Say there is a built-in variable, right, called constants, or constant, I believe. Bit vector 8 means try all possible 8-bit vector. This may take time. I don't really know whether it's going to pick those constant values. We'll have to see. Oh, I'm not sure that I commented the other one. Probably not. Oh yeah, I didn't. So let's see whether we comment this, right, and say automatically choose those constants. I haven't had much success with constant selection automatically. So I put some common constants that often occur in these kinds of problems. Okay. But the beauty is that the actual thinking is done by the machine. The human is just encoding the grammar. Okay, as you see here, it ran out of possible spaces or whatnot. I don't really know the low-level implementation details. So it was not able to come up with all these constants automatically. That's the reason I said earlier, if you're a little flexible and allow some common set of constants, usually there are only a handful of constants. So you must be open to more flexibility if you're looking for good results from a tool. Okay, all right, so to sum up, I clearly explained hopefully how division by 16 works using a synthesizer that automatically came up with this beautiful formula for us, right? Okay, that's all. Thank you very much.